Imagine you wake up tomorrow morning. You grab your phone to check the weather, but it says no signal. You open Uber, it crashes. You try Amazon, the delivery tracking is gone. At first, it just seems annoying. You assume a cell tower is down. You think, I'll just drive to work. But when you get to the intersection, the traffic lights are black. Cars are gridlocked. And then you try to buy a coffee, and your credit card is declined. You are wrong to think this is a glitch. This is the end of the modern world. Because while you were arguing with the barista, the New York Stock Exchange just suspended all trading. Billions of dollars in global capital have evaporated in seconds. 30 minutes later, the electrical grid destabilizes. Safety breakers trip at power plants from California to Tokyo. The lights go out. The internet goes dark. 1 hour later, every commercial flight in the air is grounded. Pilots are flying blind in the fog. Air traffic control screens are blank. Why? Because the global positioning system just died. We think GPS is a map. That is a lie. GPS is a giant, ticking time bomb hanging over our heads. It is an invisible clock that synchronizes the entire global economy. And if that clock misses a beat, civilization crashes in 24 hours. Today on Tech Layers, we are going to hack the system. We will look inside the atomic clocks that cost millions, the physics that drove Einstein crazy, and the terrifying cyber weapons that are trying to kill the signal right now. This is the story of the invisible wire that holds the world together, and what happens when it snaps. To understand the future, we must go back to the beginning. October 4th, 1957. The Soviet Union shocked the world by launching Sputnik. It was a simple polished metal sphere, emitting a radio pulse, circling the Earth every 96 minutes. While the Pentagon panicked, two young physicists at Johns Hopkins University, William Geyer and George Weiffenbach, were simply curious. They decided to listen to the signal during their lunch break. They noticed something peculiar in the radio data. As Sputnik approached Washington, D.C., the pitch of its beep got higher. As it flew away, the pitch got lower. It was a classic example of the Doppler effect, the same acoustic phenomenon that causes an ambulance siren to change pitch as it passes you on the street. They realized this wasn't just noise, it was data. By analyzing the exact rate of the pitch change, they could calculate the satellite's precise speed and trajectory. By the end of the afternoon, those two civilians had mapped Sputnik's orbit more accurately than the U.S. military. Their boss, Frank McClure, looked at their math and asked a question that inverted the problem and changed history. If you can find the location of an unknown satellite from a known point on Earth, can you do the reverse? Can you find the location of an unknown point on Earth if you know the location of the satellite? The implication was massive. The U.S. Navy was desperate. They had nuclear submarines carrying Polaris missiles, but they had a critical navigation problem. To launch a missile from the middle of the Pacific and hit Moscow, the submarine had to know exactly where it was. If the subzone location error was 5 miles, the missile would miss by 5 miles. This insight led to transit, the grandfather of GPS. It used the Doppler effect. A submarine would surface, wait for a satellite to fly over, listen to the frequency shift, and painstakingly calculate its position. It worked, but was flawed. You had to wait hours for a satellite pass. And if the submarine moved, the math failed. The military needed something better. They needed something instant, continuous, and three-dimensional. They needed to put a clock in the sky. Enter Colonel Bradford Parkinson. Today, he is revered as a father of GPS. But in 1972, he was a man in charge of a project nobody wanted. The Air Force brass hated the idea of a space-based navigation system. They were pilots. They trusted onboard radar and inertial guidance, not fragile signals from space. They told Parkinson that satellites were too vulnerable, too expensive, and frankly, too academic for real warfare. Parkinson proposed a radical new system called Project 621B. It abandoned the Doppler method entirely. Instead, it relied on a concept called trilateration based on time of arrival. The math is elegant in its simplicity. Radio waves travel at the speed of light, roughly 300,000 kilometers per second. If a satellite sends a signal stamped at exactly 12 hour seconds, and your receiver gets it at 12 hours, 0.067 seconds, the difference is 0.067 seconds. Multiply that time difference by the speed of light, and you know you are exactly 20,100 kilometers away from that satellite. This places you anywhere on the surface of a massive sphere surrounding the spacecraft. Add a second satellite, and you have two intersecting spheres, creating a circle of possible locations. Add a third, and the spheres intersect at only 2 points, one in deep space and one on the surface of the Earth. You have your location. But there was an immense engineering hurdle. For this to work, the satellite needs to know the time perfectly. An error of just 1 microsecond, 1 millionth a second, translates to a location error of 300 meters on the ground. A standard quartz watch wasn't going to cut it. They needed atomic clocks. Parkinson wanted to put cesium atomic clocks into orbit. These devices measure time by counting the oscillation of atoms, accurate to 1 second every 300 million years. But nobody had ever launched such delicate instruments on a violent rocket. Critics argued the G-forces of launch would destroy them instantly. Parkinson had to fight a war on 2 fronts, engineering and bureaucracy. He ran live demonstrations at the White Sands Missile Range using ground transmitters to simulate satellites, proving the math was sound. Finally, in 1973, the Pentagon reluctantly gave him the green light, but they slashed his budget and ordered him to use cheaper, less accurate clocks. He refused. He demanded the atomic standard, or nothing. He got his way. In 1978, the first block-eye satellite launched. The atomic clock survived the ascent. The signal was clear. Humanity had officially placed a beacon in the stars. As soon as the hardware was in orbit, a new, theoretical problem emerged. It was a battle that pitted practical Air Force engineers against the world's most famous theoretical physicist. Physicists warned Parkinson's team, "You are launching highly sensitive clocks into a high-gravity, high-speed environment. You must account for Albert Einstein's theories of relativity.